Hello and welcome to this video. In the last video, we covered topic 6.1.1, an overview of VLANs. It was the introduction to VLAN video, and it ended with the who here's the broadcast packet tracer. Today, we're going to be looking at 6.1.2, VLANs in a multi-switched environment. So when we're looking at VLANs in a multi-switched environment, we're literally talking about multiple switches. So previously, we talked about a single switch with multiple VLANs. Now we're talking about multiple switches with multiple VLANs. So the key here and the difference between this and looking at a single switch with multiple hosts is that when we connect switches together, we only use a single cable. So previously what we were doing is any interface that was connected to a VLAN, we associated that interface to the VLAN. But if we're going to be sending VLAN 10, VLAN 20, and VLAN 30 traffic over this single cable, that means that this single F01 interface on switch 1 is going to have to be able to handle all of those VLANs. And it's going to have to know that multiple VLANs are coming in and be able to send them to S3. And then S3 is going to have to know, okay, is this message going to all three of these devices or to one or the other? So if a broadcast goes out to VLAN 10, it should go to these two devices. So S1 and S3 essentially need a way of knowing which VLAN it is so we don't end up with that classic broadcast domain issue that we were having before. We're just broadcasting to things that are in the same virtual local area network. So just going to get rid of the pen tool. So that's what a VLAN trunk is. So if we look at the PC connections as branches, when we look at the connection between intermediary devices or between switches, we're looking at what we call a trunk. So a VLAN trunk doesn't belong to a specific VLAN. It more allows us to pass multiple VLANs across it. So in order to have a trunking port, we need to have a network device with an appropriate 802.1q, sorry, I just took a picture there, 802.1q capable network interface card. So that's the default on the Cisco Catalyst switches. That's what you're going to see a lot working on the 2960 switches that you guys are working on. But just be aware that Cisco does sometimes use 802.1q port interchangeably with a VLAN trunking port. So essentially 802.1q means it's able to trunk, and once you've enabled trunking, it can be considered it's a trunk port. So quite often you'll see this 802.1q show up. It's something you want to look for if you're setting up a legacy switch or you're setting up and designing a network and it's not a Catalyst switch. Make sure it has that if you know it's going to need to trunk. But if you don't, in the case of packet tracers in this course, for the most part, every switch you're going to actually, for all the cases, all the switches you're going to use are going to have 802.1q capable connect ports. So you're just going to be able to enable trunking on them, and that's not going to be a big issue. Okay, so I'm just going to remove this. So a network like this wouldn't be able to function without VLAN trunking enabled because the switches they need to know which VLAN it is, as I said before. So how do we control the broadcast domain? We kind of looked at broadcast domain quite heavily previously. So I'm going to send a broadcast from PC1, which is a faculty computer, and we only wanted to send it to PC4, which is also a faculty computer. We would need to configure a VLAN. Now, when we want to configure that VLAN, we need to be able to send because we don't want to send it to student and guest on PC2 and PC3, PC5, and PC6, we need to configure our VLAN, and we need to set up our trunking so that S2 can say, hey, here's a broadcast, but also it's not going to all of these devices. It's just going to this one VLAN. So it needs to tell S1 which VLAN it's on, and S1 needs to tell S3 which VLAN it's on. Let me get rid of the pen tool. So the crucial thing here is that VLANs are restricted to the devices that are on that VLAN, and that S2, S1, and S3 need to be able to say, hey, here's a broadcast frame, and also this frame belongs to this VLAN. And how does it say that, and also this frame belongs to this VLAN? Well, it just adds in what's called a tag or a VLAN ID. So what it does is between the source and the type length, it adds a tag. That tag contains the information about what it's being transmitted on. In this case, the 8100 means Ethernet. You don't really need to know that for this course, but just a fun fact, I guess. So It also lets user priority information. It gives you some mechanical format identifier information, but what we really care about in this course is that VID, that VLAN ID, a 12-bit VLAN identification number that supports up to 4,096 VLAN IDs. Later in this course, you'll get some examples of what VLANs you should be using and which ones are sort of restricted or set aside for specific purposes. But there's 4,096 available. So now that the frame has a section in it that says what VLAN it is, all the other switches in the network who receive that frame can check what VLAN that's going with. So when that happens, the frame check sequence is also updated as a quick note. So remember, the frame check sequence allows the switch to check that it's essentially a hash of the frame that allows the frame the switch to check if that frame is complete or if it's been damaged at all. So in store and forward switching, it would read the whole frame, check the FCS, make sure it was okay, and if it was okay, it would forward the frame. If the FCS hash didn't match the hash that it calculated based on the frame it received, it would drop the frame because it was corrupt. Similar switches are still dropping frames that are runt frames or smaller than 46 bytes. So, okay. So when we're looking at, so that seems simple enough. We configure trunking, and then the VLANs can communicate with each other because each switch has a way of knowing which VLAN it belongs to. So what happens to that native VLAN we talked about? We talked about this native VLAN that handles untagged frames. And we were like, well, what's a tagged frame? Well, now we know what a tagged frame is. So when we look at tagged frames on the native VLAN, so the first thing here is that if the native VLAN receives, if anything on the native VLAN receives traffic tagged for like VLAN 1 or VLAN 2, VLAN 3, any other VLAN, it drops that frame because it shouldn't be on the native VLAN, and it's assuming it just got sent there accidentally. So we want to make sure that we're not sending any tagged frames on the native VLAN. And note that the default native VLAN is VLAN 1. So if we're planning on using VLAN 1, we need to make sure we reconfigure the native VLAN. So devices from other vendors that support tagged frames on the native VLAN include IP phones, servers, routers, and non-Cisco switches. So Cisco is fairly, if it's native traffic and it's VLAN traffic, it's going to be dropped, but be aware that some other devices are not, right? So if the VLAN ID is the same as the native VLAN, that traffic is getting dropped in Cisco. If the traffic is untagged, and I'm going to add a little caveat here, we shouldn't have untagged traffic. If there's traffic on our network, it should be coming from a VLAN that we have assigned. If there's untagged traffic, that means we just got lazy and didn't assign traffic, or we didn't assign it if we're designing a new network. So we're not going to see native VLAN traffic on a newly designed or well-designed network. Okay, we are going to see it on legacy networks. So if you go into a really old network system and it hasn't been updated or there's some changes, you are still going to see that non-VLAN traffic, especially if it's using control devices that don't have the ability for some of this stuff. So that's why we still talk about it. That's why we still support it, because we always want to be able to support backwards compatibility, but we shouldn't be designing for it. So when we're looking at native VLAN traffic, so for example, PC1, not on a VLAN. So its traffic is going to get sent over the network. So it sends it to this hub, which is, to begin with, a terrible network design and clearly a sign of a legacy network. And that hub just sends it to everyone, because as we know, hubs just like to spread their data. And these devices send the traffic. So if VLAN 1 is your native VLAN and it hasn't been reconfigured, any traffic from PC1 is going to get sent to VLAN 1. Now, if we don't want that to happen, we need to make sure we've configured our native VLAN 1. As we said in the last video, the standard that we configure native VLAN 1, or native VLAN 2, sorry, is VLAN 99. So the native VLAN gets set to VLAN 99, then we won't have that overlap with our existing VLAN 1. And also, when this switch receives native VLAN traffic and VLAN 1 traffic, and that's the same, VLAN 1 has the same ID as the native VLAN, it's going to drop those frames. So you're not going to get any messages actually passing through VLAN 1. So just something to avoid anyway. I'm going to remove that. Okay, so that's what they're getting at here. This is all about setting up legacy Cisco even says what I said about a hub. It uses a hub, has a host connected to a trunk link, and it implies that the switches have access ports assigned to the native VLAN. So if VLAN 1 is the native VLAN, that's bad. We want to change that because otherwise we're going to have weird issues with switches dropping frames. And also we don't want native traffic. We want to limit that as much as possible because native just means like that's where it originally came from. And we want it to come from a specific VLAN we've set up. So 802.1q trunk, we don't want to have native traffic on it unless it's a legacy system, in which case it's kind of unavoidable. We avoid hubs as much as possible, and we don't connect hosts directly to intermediary devices. It's just not good practice. There's no way to control it. There's no way to set up switch port security, really, if it's not going through a switch or some sort of device like that. So native traffic VLAN handling exists to support legacy systems, but we don't need to really set up a lot about it. We just need to make sure that VLAN 1 is not the native VLAN. So a separate voice VLAN is required to support VoIP. So VoIP traffic needs to take priority. It needs to be not having delays in it. It needs to have be connected through the switches quite quickly. So we want it to have its own VLAN. IP phone can be configured to use 2 separate VLANs. Now, if you look at, I don't really have an example of this in our class, but I can show you on my phone. So the Cisco VoIP phones that the school has, for example, in most classrooms, the internet line, so the Ethernet cable that connects to the school network runs into the phone, and then it runs from the phone into the teacher's desktop. So that's how the teacher's desktop gets network, which means that if we want our VoIP traffic to be on a separate VLAN, we are going to want that single cable going into the wall to have 2 VLANs. So the phone itself has the ability to allow us to have this multi-VLAN system. I'm going to tell you right now that I'm pretty sure the school does not have a separate VoIP VLAN, which is not the best network design, but it is the network design we have. The reason it's not set up like this in my room is because obviously my desktop is not plugged into the school network. It's plugged into the CompWorks network. My phone, on the other hand, is plugged into the school network so that I can receive emergency phone calls. I have the emergency power layer, and also just so that I'm connected into the internal phone network and we don't have any issues, because our phone system is set up so we can network not just within the school by dialing a couple digits, but we can network throughout the whole district. So it is possible to configure through a Cisco IP phone, a VoIP phone, in order to handle the layer priority of the VoIP traffic differently than of a PC traffic, because as you can see here, that it is one cable going from the switch to the phone and one from the phone to the PC. And if you look in most of the classrooms, if you look in like 215 or most of your teachers' classrooms, that's how the setup is going to be. But again, this is not a good classroom for that example. So you can go in and you can configure the switch ports for that. In terms of this course, you should know that VoIP phones have this capability, but you don't need to know specifically how to configure it. You can go on to Packet Tracer and play around with configuring the VoIP phones. I'm sure that Tom will, but you don't have to know the specifics of that, or even the configuration specifics of that. You just need to know, okay, if a VoIP phone is running the Ethernet line out to the desktop, it is possible to put them on separate VLANs, and you definitely need to know that voice traffic should be on its own VLAN in a good network design. This Packet Tracer investigating VLAN implementation is a very good one for going through and practicing the VLANs. So I'm going to stop the video here because I would like you to do this activity, and I would like you to attempt this Packet Tracer, right? So add that into your lab files and do that. And then in the next video, we'll go on and cover 6.2 VLAN ranges and other sorts of VLAN information, and actually get into configuring VLANs. So work on that Packet Tracer and then start up the third video.